in this first example, we will study the behavior of a ceramic sample. So some data have been recorded when pulling on a ceramic sample, and we have already the information that we have is the strain and the stress. So a force was applied and the displacement was recorded, and it was already transferred as strain and stress. That's what we want to draw, to plot our curve, stress strain. So let's start to do that. We will select all our data, select also the two axis titles, and click on Insert, Chart, and we will get the charts. And there's different options that we can use. We can use, you see on the right, line chart, scatter chart. The bar chart doesn't make sense. The area chart, or also the smooth line chart. Sometimes we see that as like all the points have been smoothly linked together. For these problems, I will use the area charts because we have some area to find later, to find the modulus of resilience and the modulus of toughness. So I think it makes sense to see those different areas. I like to add on customize series the data label. Here we go. So we have the informations of the stress for any strain. And close. So here we go. So the first question is, what is the Young modulus, the modulus of elasticity, knowing that the elastic regions is just between the 0 and the first point. So until the 33.2 stress value, that is at an elongation, not an elongation, a strain of 0.0006. So Young modulus will be the delta y divided by the delta x. So will be equal to, the delta y will be the 32.2 minus 0. So the 32.2 divided by the delta x, that is the 0.06, 0.0006. Enter. So this is your Young modulus, and this is in KSI. So we found the 55,000 KSI is the Young modulus of the ceramic. Second question, find the modulus of resilience, and the modulus of resilience is, up. Let me move that down. That would be the area below the first line, just below the elastic part. So we are there. This is this triangle there. Okay. So area of a triangle, that will be the 8 times the base divided by 2. So the 8, 32.2 times the base, that is the 0.0006, and divide by 2. Enter. So this is the modulus of resilience, and you see if we keep it in inches times pi per inches cube, it's very small. So let's put it in with the pound instead of the kilo pound. So this one time 1,000. So 9.96 inches times pound per inches cube, modulus of resilience. And now we have the modulus of toughness to find, and this one is equivalent to the area below the curve, the full curve, all of that. There is different way to find this area. You can count the rectangle, 1, 2, 3, 4, 5, 6. The smaller they are, the closer, the more close to the answer you are. We can find maybe the function of the curve and take the integrations, all of that. Just remember that it's always an approximation anyway. So in our case, I will propose to add the different area, the triangle, the rectangle plus the triangle, the rectangle plus the triangle, etc. Because it's kind of fast in Excel because we can drag the different formula. So the area 1 is this one, okay? That will be the triangle again. So the 33.2 times the strain divided by 2. It is the first area. The area 2, don't click enter. The area 2 is different. That will be the rectangle plus the triangle. So the rectangle will be the 33.2 times the delta x. So 33.2 times the delta x, this one, minus this one. So this is the rectangle, plus the little triangle. So the little triangle will be the 45 minus 32.2, so the delta y divided by the delta x. So the delta y, the 45.5 minus 33.2 times the delta x, the 0.001 minus 0.106, and don't forget that's a little triangle, so divide by 2. This is the area number 2. And this formula, we can drag it. So if we drag, that will take the next one, and the next one, and the next one. Up. Here we go. So you see, if we look at this one, for example, this formula with the 7 and the 8 rows, that's between those values. And okay, I already plugged that formula, but this one is the sum of all the area. Oops, I did the sum of all of them. And because if we keep it in inches time kilopounds per inches cube, it's a bit small. I multiply the value by 1,000, and I got the module of toughness in inches time pound per inches cube. So this is 3 of the mechanical property that we can find with the curve, with the diagram stress strain. There's a lot of other ones. We will see that in next problem. And oops, I will just show you the full answers with this one next to it. Here we go. That makes sense. Let me know if you have questions. Bye-bye.